Hi, my name is Jensen Jiaxin Lim, and this is Physics 1 Lab 3. In this lab, we're going to simulate the motion of a spaceship to determine its inertial velocity for a safe investigation of the black hole and its environments. Through this, we're going to estimate the mass of the black hole by analyzing the orbit of a star, and then we're going to determine the gravitational forces of the black hole and the planet, and we're going to determine the inertial velocity of a spaceship when it leaves the surface of a planet without crashing onto the planet and into the black hole. So this is the preview of the results for part 1 and part 2. So here are some important formulas that we'll be looking at in this lab. So one of them includes Newton's law of gravitation, which shows F equals gmm over r squared, where g is the gravitational constant, m1, m2 is the mass of the planet respectively, and r is determined by the distance between the two planets. We'll be also looking at Newton's second law of motion through the position update formula and the velocity update formula. And we're also going to be looking at the momentum principle, which is shown with the change in momentum divided by the change in time. And last but not least, we're going to look at a new formula, F net perpendicular, which is represented by F equals to mv squared divided by r. So here are other important formulas to know as well, which is the parallel and perpendicular forces. So the parallel forces acts in the same direction, either aiding in acceleration when aligned or creating equilibrium when opposing. And the perpendicular forces acts at right angles and can induce rotation or torque when unbalanced, contributing to angular motion. So for the first part of the experiment, the system will include the star and the black hole, and the surroundings will include the gravity and space. So the velocity of the planet was randomized to create individual values, and the mass of the planet is set to be 2 times 10 to the power 30 kilograms. So using the delta of 1 day, the net force acting on the planet from the black hole will be calculated from the randomized velocity in the parallel and perpendicular directions. From this, average mass of the black hole can be calculated. So the code here will simulate the trajectory of a star orbiting a black hole, and the code below will give us the net force as well as the F net perpendicular as well as the F net parallel. What we concluded is that the F net in total is 8.829 times 10 to the power 28 newtons. The F net parallel is 1.43849 times 10 to the power 28. F net perpendicular is 8.70339 times 10 to the power 28. And the mass of the black hole is 7.71 times 10 to the power 33 kilograms. We can conclude that the experiment shows the star follows an elliptical orbit around the black hole due to gravitational force on the star. And as the star gets closer to a black hole, the magnitude of the component increases compared to the star when it is further away from the black hole. Some errors to take into account is that I should have run the program longer in part 1 to achieve a more accurate average mass. And also rounding errors of the initial conditions could be significantly off from the real conditions. So for experiment part 2, we'll be finding the initial velocity of the spaceship as well as the shortest distance of the spaceship towards the black hole. The system includes the spaceship and the surroundings will be the planet and the black hole, and the picture shows other initial conditions of the experiment. So the code below incorporates conditions to avoid crashes, such as getting too close to the black hole and crashing into the planet. The trajectories that we calculated further provide insights to how the black hole affects the spaceship, and we can see further that the ship speed that we chose and the different forces that we can act on. So these are the results of the shortest distance and the initial velocity of the spaceship for a time of 60 minutes. So the analysis shows that the spaceship goes out of orbit as it leaves the planet due to gravitational forces of the black hole. Some errors is that we had to use trial and error method for the initial velocity in part 2, and another error includes rounding errors of the initial conditions, which could be significantly off from the real conditions, just like the first part. So some questions to think about include what rate of change of momentum means and what net force means. So perpendicular and parallel components of each are mathematically the same, but the direction of the F net perpendicular and parallel are easy to observe, but its magnitude is harder to measure, whereas the rate of change of momentum is easy to observe and measure, but as it only needs the object's mass, velocity, and time interval to calculate. Another question is if we decided to enter into an orbit around a black hole. How to do this? Well, we could lower the velocity in the x component, and we're going to have a similar velocity in the y component as originally. And that will be about, for the x direction, it will be about -2 times 10 to the power 6 meters per second, and in the y component, it will be 0.75 times 10 to the power 7 meters per second.